All right, well, good morning. Welcome to another fun-filled day of trig. You may remember last time what we did is we developed some identities. We looked at the identities for the sum and difference of angles. So there's a lot of geometry, a lot of algebra going on. But we developed a set of identities. I'm going to remind you about those at the start today because we're going to build on them. We're actually going to take those and build a whole bunch of other identities, a bunch of groups, including what we call the double angle identities, the power reduction identities, the half angle identities. So they're going to be a whole bunch, but they all go back to the ones that we developed last time. So like I said, we'll start there. But before I get to that point, are there any homework questions? Things going okay in general? All right, well, again, I'm going to take silence as things are going okay, or at least you're not ready yet to ask me a specific question, which is fine. So then let's go ahead and just sort of recap where we were, what we did last time, and where we're heading today. So I'm going to go back to the board real quick. And let me write up the identities that we built last time. So these are the sum and difference of angles identities, and we have a whole bunch, but I'm going to actually combine these into their pairs because we saw, for example, that the signs, the one when we added and subtracted, were very similar. In fact, the only difference was a plus or minus sign. So I'm going to write this as sine of A plus or minus B. That way I can kind of write both of them at the same time. All right, I'm going to need to make them a little smaller, or else I'm not going to be able to fit it. Okay, so here's what we saw, that for these, the forms, we had sine of A, cosine of B, and the other one was sine of B, cosine of A. And the way I'm going to write this is, since one of them was positive and the other one was negative, I'm going to go ahead and write that as another plus or minus. Okay, so the way to read this is sine of A plus B was sine of A cosine of B plus sine of B cosine of A. And then similarly with the minus, A minus B is sine A cosine B minus sine B cosine A. So we got this last time for sine. Also, for cosine, we saw that those two were also a similar form. So I'll go ahead and just combine them again. And what we got was cosine of A times cosine of B. And then we had sine of A, sine of B. And again, the difference was the signs, but I'm actually going to write this one as minus over plus. Now, you may not have ever seen this before, a minus over a plus. So just like we have plus or minus, this is called minus or plus. But basically, the reason that I had to turn this over is because the positive in the cosine here ended up giving us a negative in the identity. So the way to interpret this is that the positive, the top one, corresponds with the top one in both cases, and the bottom one with both. Okay, so that's what the cosine ones look like. And then the tangent ones, we ended up getting a fraction. And it was tangent of A and tangent of B on top. And then we had a 1 and a tangent of A times the tangent of B on the bottom. And on top, the plus or minus was the same, but on the bottom, it was the opposite. So for these guys, the sign on top corresponds to the sign in between, or in the original, and then the one on the bottom is the opposite. So that's why I'm going to write it as minus plus. All right, so these were the identities that we built last time, and we played around with them. We used them to calculate some angles that we hadn't done before. So we were able to find things like the sine of 7 pi over 12, or things like that. We also played around a little bit with the inverse trig functions and stuff like that. But these are those identities. Okay, so hopefully you've got these written down somewhere so you can reference them, because we are going to use them. But I'm going to have to eventually erase them off our board. All right, so here's the goal for today. Here's what we're looking for. We're looking for the next set that I'm going to call the double angle identities. And they are exactly what they sound like. They're going to be an identity for sine of 2 theta. And there's going to be an identity for cosine of 2 theta, and an identity for tangent of 2 theta. So this is our goal, because we're going to want to be able to write out an equation for each one of these. But I do want to warn you, just to prep you ahead of time if you're like trying to make space on your paper or whatever. For the cosine of 2 theta, we're actually going to have 3 forms for this one. So there are actually 3 different things that you can make the cosine of 2 theta equal. I will show you all 3, and we'll talk about why we care about all 3. But this is the goal, at least for the start of today. All right, so here's the question then, and this is a question I'm going to pose to you guys. What do these ones that we developed last time have anything to do with the double angles? Like, how are we going to use what we did last week to do double angle identities? Any ideas or thoughts? So this is when I have my Bueller moment. Anybody out there? All right, at least I'm getting a thumbs up. Mariola's here. Cool, thanks, Mariola. Appreciate that. Okay, well, how about this? Think about what 2 times a number means. What are we really doing when we double a number? Okay, so Amber said we're making it bigger. Yeah, we definitely are making it bigger. And then Mariola put, we're adding the same number twice. So that's really what happens with multiplication, is it's repeated addition. So sine of 2 theta, it's actually the same as saying the sine of theta plus theta. So we're just taking a number and we're adding it with itself. So in this case, we got theta. We're going to add it to itself. Okay, but now we've got a sum of angles, which means we can jump up here and use the sum of angles identity. So what we're going to do in this formula is everywhere there's an A, we're going to put theta. And everywhere there's a B, we're going to put theta. So this is going to look like sine of theta cosine of theta plus, I'm using the plus because it's the top one, it corresponds to the plus over here. And on the other side, we're going to get sine of theta cosine of theta. And so notice that those two are identical. We've got sine of theta times cosine of theta plus another one of them. And so what that gives us is the double angle identity for sine. And I'll go ahead and box it, because of course when it's in a box, we know what to remember. But there's our double angle identity for sine. The sine of 2 theta is equal to 2 sine theta cosine theta. So what this allows us to do is actually take a bigger angle and relate it back to the smaller one. So there you go. I know that before I was telling you about the Pythagorean as the one identity everybody remembers. This is a close second. Sine of 2 theta equals 2 sine theta cosine theta. When I say it's a close second, I probably shouldn't say it in terms of people remembering it, but I'm going to say it in terms of it's one you should remember. We use this in calculus all the time. This one identity can make calculus so much easier. So sine of 2 theta is equal to 2 sine theta cosine theta. All right, well, we'll play with that later. But while we're at it then, let's get the double angle identities for the others. So I'm going to skip cosine for a second, since there are 3 forms. Let's just jump to tangent, and let's see if we can get the double angle identity for tangent. So similar idea. This time we're going to look at the tangent of 2 theta, which is going to be the tangent of theta plus theta. So let's use the identity. Let's use the sum of angles identity for tangent to see what this has to be. So on top, we're going to get the tangent of theta plus the tangent of theta. So if you go back to that identity, I'm plugging in thetas for both A and B. And then on the bottom, we're going to get 1 minus tangent of theta times tangent of theta. So again, the sign on top matches the sign inside of our tangent, and then the bottom one is the opposite. So we can simplify this a little bit, and we get 2 tangent of theta on top and 1 minus tangent squared on the bottom. Okay, so I'm going to go ahead and box this as well, because there's our double angle identity for tangent. But just like the one for sine, it's relating back to this smaller angle, the angle that was half the other one. All right, so any questions so far? Hopefully this is pretty straightforward. We're just using the identity we developed last time. And we're just making those 2 things the same. They're both thetas, and so let's see what happens. All right, so I know this isn't very exciting. Well, at least the next one, there's going to be some variety to it. So let's go look at the cosine of 2 theta. And we'll do exactly what we just did, but with cosine. And then we'll also talk about why there are 3 forms of it. So we've got cosine of 2 theta. Of course, that's the same as cosine of theta plus theta. Starting exactly the same way. Okay, so now if you go and you look at that form, we had cosine of theta times cosine of theta. Okay, so Diego, you just said this is for adding angles. What we're doing right now isn't for adding angles, it's for doubling angles. We're using the identities we developed last time for adding angles. All right. So if we go back and look at that identity for cosine of A plus B, it was cosine A times cosine B, and then it was minus sine A times sine B. So we're going to have cosine times cosine minus sine times sine. And so here's the first of the three forms for the double angle identity for cosine. So we've got cosine of 2 theta is equal to cosine squared theta minus sine squared theta. So let's go ahead and put a box around that. But this is form number 1. Okay, it's form number 1 because there are a couple others. Now, this one probably looks a little familiar, but I'm going to warn you. It's not what you think it is. It looks a lot like the Pythagorean, right? But what's the difference between this and the Pythagorean? Good, well, yeah, a lot of you are throwing it in there. It's a subtraction, right? We're subtracting instead of adding. So it's not the Pythagorean. The reason I bring this up is we're really used to looking at sine squareds and cosine squareds and turning them into a 1. Well, now you're going to start seeing them when they're subtracted, and I want you to realize that that doesn't mean 1 anymore. That actually means the cosine of 2 theta. All right, well, it is what it is, but this is one form of the cosine of 2 theta. Now, the reason that this has other forms is because of those squares and because we can use the Pythagorean, right? Remember your Pythagorean says sine squared plus cosine squared equals 1. We could actually say solve that for sine squared, and we could substitute that up into this formula we just created. And check out what happens if we do that. This thing turns into cosine of 2 theta equals cosine squared minus 1 minus cosine squared. And if we distribute, we can rewrite this then as cosine of 2 theta equals 2 cosine squared theta minus 1. So hopefully you see where the minus 1 came from, and then the 2 cosine squared came from the 1 minus the negative, gives us a plus 2. All right, so there's form number 2. So both of those are identical. I know they don't look like it, but they are equal to each other. So having one or the other is perfectly fine. So before we get to the why we care about having another one, let's get the third one. And I bet you can guess what we're going to do to get the third one. What do you guys think? What could we do to change this into a third form? Yeah, how about we solve for cosine and substitute? So instead of doing this where we got sine squared equals, we could have done cosine squared. We get cosine squared is equal to 1 minus sine squared. So if we were to put that in, we'd get the cosine of 2 theta is equal to 1 minus sine squared minus sine squared, which then when I combine gives me a 1 minus 2 sine squared. So we'll go ahead and box that one. And there's our third form. Okay, so like I told you, like I promised, there are actually 3 different forms for the cosine. And there they are. Okay, so why do we want 3 of them? I mean, they're all equivalent, right? Like, if all we're doing is we're making use of the Pythagorean, we're going to get the same thing. It's going to be worth the same amount and all that. So why would we have 3? Can you think of why it might be advantageous to have one of them as opposed to the others? Well, how about this? Think about the first one. So suppose I asked you to figure out the cosine of some angle that's twice another. What do you need to know about the original angle? What do you need to know about theta in order to actually use the first one? And this isn't a trick. You need to know its cosine, and you need to know its sine. So you actually need to know two things about that angle. Well, if you look at the others, you don't need to know two things. If all you know is cosine, cool. The second form, we're done. If all you know is sine, use that last form. And so this is going to come in really handy in those situations where we actually have to find the trig values to plug in. And if we're using either the second or third form, then we only actually have to calculate one of them. So let me show you what I mean. All right, let me give you an example here. And we'll start playing around with all of these identities, the double angles of sine, cosine, and tangent. All right, so here you go. Let's say I told you, or this is what I want to know. I want to know what the cosine of 2 theta equals when we know that the tangent of theta is minus 5/2, and theta is in, say, quadrant 2. So I didn't tell you anything about theta, or the cosine of theta. You don't know anything about what number it is, what that angle is. We do know where it is. We know it's in quadrant 2. So that's kind of useful, maybe. But we want to find the tangent, or the cosine of 2 theta, given that the tangent is minus 5/2. Okay, so think about what this means. We have to do one of two things. We either need to find cosine of theta, or we need to find the sine of theta, or we need to find both. So those three different forms for cosine of 2 theta, the first one was number 3, and then the second and third were the top 2. All right, so either way, we got to figure out one of the cosine or sine, but we could also just find both of them and plug them in. Okay, well, this is definitely a situation, and hopefully you're on board with this, where I just want to do one or the other. I either want to find cosine or I want to find sine. I don't want to bother with both. All right, well, since it doesn't really matter which one we find, let's just draw the triangle and see what we get. So remember, what I'm drawing here is the reference angle. This isn't theta. Theta's in the second quadrant. This is the first quadrant. Okay, but I'm going to use this to help me figure out my cosine or my sine. Now what I'm going to put on here are the side lengths 5 and 2, which came from my tangent. So hopefully you're starting to get comfortable with this. When we're given a trig function, we use that value to start building the right triangle. We've done that quite a few times. right? So that'll continue happening. But since I've got those two sides, I can find the third side using the Pythagorean theorem. And I think with this one, it gives us the square root of 29. Right? 5 squared plus 2 squared is 29. So that's the square root of 29. Okay, so which do you want to find? Cosine or sine or both? All right, so William just said cosine. We'll take that as our first person who speaks gets to pick. So let's get the cosine of it. So what's the cosine of this angle? All right, so get Amber, it's 2 over the square root of 29. It's adjacent over hypotenuse. However, it's either the positive or the negative of that. Remember what we just found was the cosine of the reference angle, which means the cosine of our angle is either that number or it's negative. So which is it? Is it the plus or is it the minus? All right, so we got a couple of real quick votes for negative. Bella and Will and Amber. Diego saying positive. Now Amber gave us a reasoning, right? She said minus because it's in quadrant 2 with the question mark, and then Bella just kind of backed that up by saying X is negative in the second quadrant. And in fact, yes, we know for sure that this actually is negative because of the fact that we were in quadrant 2. So we always have to be careful with that. When you draw your little right triangle, that's cool, do it. But then always check yourself, plus or minus, because it matters where we're located. Okay, so cosine is actually equal to negative 2 over root 29. Okay, so since we've got cosine, that's sufficient now for us to find the cosine of 2 theta. Because we've got an identity, it says that the cosine of 2 theta is equal to 2 cosine squared theta minus 1. And so what we're going to do is we're going to put that value that we just calculated for our cosine into this formula. So we're going to get 2 times negative 2 over root 29 squared. Okay, so Aries, you just asked, why didn't I draw the right triangle as if it was in the second quadrant? Okay, the reason I didn't do it is a couple reasons. One, I like to be really, really systematic, do it the same way every time because I know some students really like that. And so if I always draw it in the first quadrant, then it's always going to look like that, and we don't have to adjust the signs as we go. The other reason that I don't actually do it in the second quadrant, let me just show you real quick. If I had done it that way, so here's my triangle, and I could have set it up with the tangent stuff, but here I'd have to remember which one is positive and which one is negative, which that's okay, right? I mean, we're gonna have to deal with that sometime. But the problem is that this isn't our theta. Our theta is actually this guy. And while it does lead us to the same answer, I have a really, I personally have a hard time doing this because that's not my angle. This is my reference angle. And so if I'm going to deal with my reference angle, I just go back to the first quadrant. So in terms of why I did it this way, personal preference, it's totally fine if you want to draw it in the second quadrant. Just make sure you keep track of which ones are positive and negative as you're building your right triangle. So real quick, I don't know if you figured this out yet. You guys are pretty far in math now. But math, there isn't one way of doing math, and you can always craft it to be your own thing. I actually liken it to like art. Everybody that, you know, is a painter, they all learned about colors, they all learned about brush strokes, they all learned about, you know, techniques and blah, blah, blah. But then when they actually go and they do it, they put their own spin to it. And it's the same thing in math. Like, you're learning all the techniques. You learned how to factor, you learned geometry, you learn, you know, all of that. But now that you apply it, you can do it any way you want. So anyway, just realize that. And then Isabella just said that math's a language, and that's true too. It is a language, and not all writers write the same way, even though we all use English, right? So language is art, maybe. I don't know if language is art. Writing and literature for sure is. But there's plenty of writing that's not art, just like there's plenty of math that's not art. Don't get me started on statistics. And I just realized I probably shouldn't have just dropped that bomb and left. Stats is perfectly fine. It's just, in my opinion, it's not math. You use numbers, absolutely, but you're not doing math. Just like a house painter, they use paint, but they're not artists. Right? But anyway, don't get me started. Hey, we've all got our things, right? Anyway, so let's get back to this problem now that we've got our cosine value. All right, so we got our cosine was minus 2 over root 29. We go ahead and we plug that in. We'll go ahead and square it. And we end up with 2 times 4 over 29 minus 1. And I can go ahead and get a common denominator here. So that's 8/29 minus 1, which is negative 21/29. So check this out. We don't know anything about 2 theta. I don't know where it is. I don't know, you know, what the coordinates of the point on the unit circle are or anything. I know nothing about it. And yet I was able to figure out its x value. So wherever that angle is, it actually intersects the unit circle with an x of minus 21/29. Now, one more piece of good news for you here, and this is really only true for the cosine double angle formula. Notice that when we got the cosine, we squared it, and we are going to get the same number whether that cosine is positive or negative. Right? You square anything and it turns positive. So there's some good news for you. Remember how I was like, well, don't forget what quadrant you're in so you can get the right value. It turns out it's irrelevant if you're using one of the last 2 forms of the cosine of 2 theta identity. Same thing would have happened with the sine. It didn't matter, since with that formula, the sine is being squared. That's another reason why I'm a huge fan of these alternate forms, even though it's not an issue with the first form either, since you're squaring both cosine and sine. But anyway, so there you go. So there's an example of where we could use this, where you know something about the original angle, but you don't know anything about the double angle. And maybe that's what you're actually interested in. Okay, so let me show you another place where we could use this. Let's actually do an identity. Let's prove an identity using these. But I'm going to be sneaky. I'm going to actually be a little mean. I'm going to give you an identity that involves the not big 3. So let's see if we can prove this, or we're going to confirm the identity. So we're going to show that this must be true. And this identity is the cosecant of 2x minus the cotangent of 2x. And what we want to do is we want to show that that equals tangent. All right. So remember what we do for identities. We pick the uglier side, we do stuff to it, trig and algebra, until eventually it looks like the other side. All right, now for this one, I think it's pretty clear which side is uglier. I would argue the left. So I suggest that's where we start. We see if we can fiddle around with that one so that it ends up looking like tangent of x. All right, so where to start? Obviously, we can't just start with the double angle identities because we don't have identities for cosecant and cotangent. So probably what we should do first is maybe turn them into trig functions whose identities we do know. So how about we convert those guys? So let's make the cosecant. Let's make that 1 over sine. So this is going to be 1 over sine of 2x. So we know what to do here. We know what sine of 2x looks like. All right, so then what about the cotangent? What do you want to do there? Okay, so Amber just said cosine over sine. How about 1 over tangent? No, no one wants to fall for that one. I mean, we could. It totally would be the same. It's going to be a little bit faster if we just make it cosine over sine. Because notice that if we turn this into cosine over sine, already I can combine these into one fraction. They already have the same denominator. So I can do a real quick algebra step. So this is starting to look pretty good. Okay, so Amber, you said, so is regular tangent sine over cosine? Yes. So cotangent would be cosine over sine? Yes. And that's actually what I did here, cosine over sine. You were right with what you wrote. All right, so now let's deal with these double angles. I want to get rid of those two x's because where we're going, remember where we're going, use this as your roadmap. We need to get rid of the, we want just x in there. So we need to get rid of those 2's, which means we want to use double angle identity. So on the bottom, for example, sine of 2x is going to be 2 sine x cosine x. And then on the top, we're going to have 1 minus, but this is now where, we have 3 choices. Which of the 3 do we use? It turns out it doesn't really matter. We can pick any of them, but we can save ourselves some time if we pick the right one. So the question is, which of the 3 forms do we want to use here? Do we want the cosine squared minus sine squared, the 2 cosine squared minus 1, or the 1 minus 2 sine squared? So Amber suggests the one with the sine in it, the 1 minus 2 sine squared. Well, since you were the first one to speak up, I'll let us pick yours. So we'll go ahead and put 1 minus 2 sine squared x. Now, before we go further, was there a reason you picked this one, Amber?
Originally, it was to cancel out the signs, but now that I'm seeing that the square is there, it's different than I originally thought.
Okay. But I definitely like that idea where you said, oh, maybe we can cancel out a sign, because we don't want a sign on the bottom, right? Eventually, we're getting just a tangent, and tangent would be sine over cosine. So getting rid of that sign would be good. Alternatively, same thought process, tangent has sine on top. Well, I might as well just make it so I've got sines on top, because if I put cosines in there, I'm going to somehow have to get rid of them anyway. Well, let's see what happens. So when I distribute that minus sign, the ones cancel, and then the minus minus gives me a 2, positive 2 sine squared x. And that's going to be over 2 sine of x times cosine of x. And now one of those signs cancels. The sign on bottom is going to cancel with one of the ones on top. The 2's also cancel. And if you look at what we're left with, we've got just sine over cosine, which is tangent of x. All right, well, there you go. We were able to confirm that identity using the other double angle identities. All right, so how are you feeling about double angle identities? They all right? Cool, I'm getting some thumbs up. Just realize that they come exactly from the sum of angles identities. All right, well, let me show you the next set of identities. Now that we did the double angle identities, the next set I want to show you are what we call the power reduction identities. And they're going to do exactly what they sound like. You notice the double angle identities, we're all about having a double angle. Power reduction identities are going to take powers of trig functions and reduce them down. Okay, so they're going to be ones that say sine squared of theta equals cosine squared theta equals tangent squared theta equals. Okay, so we're going to start with squares, and we're going to see how can we reduce them down so that we don't have squares anymore. So you can probably already see one of the reasons we might want this is because it's a lot easier if you don't square numbers, right? Especially if those numbers are gnarly. If I can get away from squaring it, that might be useful. Okay, so this is what we want. We want things that look like this. Now, it turns out that what we're going to use are the double angle identities, because the double angle identities had these things in them. Specifically, look at the cosine double angle identity. So we had like 3 forms of it, right? Well, if you look at that first one, or not the first, sorry, the last one, we had the cosine of 2 theta was equal to 1 minus 2 sine squared. So what I'm going to do is I'm actually just going to solve this for sine squared. So we'll just move some things around here. So we get 2 sine squared theta equals 1 minus cosine of 2 theta. And then the last thing we have to do is divide by 2. And that, my friends, is our power reduction identity for sine. So what it's doing is it's taking it from a squared trig function to a trig function that's just a single power. But at the same time, we are changing the angle. But this is a way to get rid of squares. If it feels like we didn't really do anything, you're right. All we did is we took this identity we already had and just solved it for a different piece. But we go ahead and write it separately as its own thing, a power reduction identity, even though it's really the same thing. All right, so there it is for sine squared. Cosine squared, you're going to do exactly the same thing, except we're going to go for the form that had cosine squared. So think about what that looked like. Let me just go ahead and erase this real quick, and we'll put in the identity that involved just cosine. This was 2 cosine squared theta minus 1. So if we do the same thing, we'll add 1 to both sides. So we get 1 plus cosine of 2 theta is equal to 2 cosine squared. And then we divide by 2. And you notice that this form is very similar. In fact, the only difference is a plus sign instead of a minus sign. All right, so that's another one that seems like it's probably nothing real. But what it does let us do is get it down into just single powers of the trig function. All right, so lastly, we need to get tangent squared. Now, tangent squared, it showed up in the tangent of 2 theta. But there was also a lot of other crap in there. Instead, let's just go back to what we know about tangent, and that tangent is sine over cosine. So what we can do for this one is take the sine squared and divide it by the cosine squared. So that'll be 1 minus cosine of 2 theta over 2 divided by 1 plus cosine of 2 theta over 2. So I'm just taking the identities we just built. So if you flip this over and multiply, you end up with 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. All right, so there are your 3 power reduction identities. Even better, every single one of them only depends on the cosine of the double angle. So really, we only ever have to find out one thing. We can find out that one thing, the cosine of the double angle. We know what all of the squares are going to look like. So let's do an example where we do some algebra using the power reduction. And this is another place that I'm just going to tell you later when you get to calculus. This is another huge thing. Being able to reduce the powers makes your calculus so much easier. So let's do an example. But before we do the example, while I'm thinking about it, let me give you the word of the day. All right, so the word of today is going to be eraser. I don't think we've used that yet. So let's go with eraser for the word of today. All right, so let me show you an example what I'm talking about, why we might use this. So let's take sine to the fourth. We're going to do sine to the fourth theta. Now I'm going to call it x. Sine to the fourth x. And let's see if we can write this so that we don't have any powers. Okay, well, sine to the fourth, this is the same as saying, let's take sine squared times sine squared. And the reason I'm starting as sine squared times sine squared, the reason I'm breaking this down, is because I know power reduction for sine squared. So I'm going to do those first. So algebraically, then, this is going to be 1 minus cosine of 2x over 2 times 1 minus cosine of 2x over 2. And before you get all excited and put a little box around that, notice that we're still going to get a square. Because if I distribute this, I'm going to get 1 minus 2 cosine of 2x plus cosine squared of 2x, and all of that is over 4. So in terms of reducing powers, we're definitely on the right track. I started with a fourth power, and now I'm down to just a square. So yay. But I still have this square. So let's take care of that cosine squared. So we'll use the cosine reduction. The one that's right here, I'll go ahead and leave that for a second. So let's start writing out what this is going to look like. We're going to get 1 minus the 2 cosine of 2x. But now I need to add cosine squared of 2x. So I'm going to go to this identity. But the question is, what goes into that cosine? Does anybody see what we're going to have to put in there? And you're probably taking a pause here because you're like, wow, if he's really asking this, it's something that I wasn't expecting. Hopefully, because it's not 2x. So no ideas? Yeah, there you go. Well, it's going to be 2 times 2x. So it actually needs to be the cosine of 4x. So think about what was going on here. This 2x, that's theta. And remember what we're doing to theta is we're multiplying it by 2. So we have to do 2 times 2x, which is actually a 4x. So all of that then gets divided by 4. Whew. Well, I am going to simplify that just a little bit. I'm going to multiply everything by 2. to get rid of that fraction inside the fractions. So we're going to get 2 minus 4 cosine of 2x plus 1 plus cosine of 4x all over 8. And the one last thing I'm going to do is combine the 2 and the 1 together. And so what we're left with is sine to the 4th of x is equal to 3 minus 4 cosines of 2x plus cosine of 4x. And that's all divided by 8. But notice that now the highest power of a trig function we see over here is 1. It's just plain old cosine. It's just whatever the angles are on the inside are a little more complicated. So again, the reason that we do this kind of thing isn't really applied. It's not out there in the, we use it in calculus. We're going to use it as a step to help us do the calculus if this were to come about in an applied arena. All right, any questions on that one? All right, well, we're going to take a break because this is, I know, again, your brain is probably starting to feel a little like mush. So it's just about noon. Let's come back at 10 after. Okay, so we now have double angle identities, power reduction identities, and the last set we're going to look at today are what we call the half angle identities, which are exactly what they sound like. Now, instead of doing sine and cosine tangent of just x, we're going to have sine of 1/2 x or tangent of 1/2 x and so on. So it's really just the opposite idea of the double angle identity. We're going to go to half angles. All right, so let's build those. Go back to the board. All right, so for the half angle identities, we're going to, again, make use of things that we already know. Specifically, we're going to make use of those power reduction identities. All right, so here's how I want you to think about this is let's go back to the idea of sine squared of theta, right? That was equal to 1 minus the cosine of 2 theta over 2. Right? So we already have this. Now what I'm going to do is just a really simple substitution here. I'm going to let theta equal alpha over 2. I'm just throwing in another angle in here. We'll call that guy alpha. But I'm going to let theta equal alpha over 2. So everywhere in this identity there's a theta, we're going to put an alpha over 2. So we're going to get sine squared of alpha over 2. And that's going to equal 1 minus the cosine of 2 times alpha over 2 all over 2. So you may be wondering to yourself, why did you just do alpha over 2? Well, because I want a half angle. So I'm introducing it. Okay, so we get sine squared of alpha over 2. That's going to equal 1 minus cosine of alpha over 2. Because the 2's over here cancel. 2.5. So we're actually almost done. If I want to know the sine of alpha over 2, all I got to do is take a square root. And so here's your first half angle identity. And it's that the sine of alpha over 2, it's equal to plus or minus square root of 1 minus cosine alpha over 2. So we'll go ahead and put a box around that. But there's your half angle identity for sine. So if you cut an angle in half, you actually need to know about the cosine of the original angle. But with that, you're going to be able to find the sine of that half angle. But of course, I'm going to warn you. Okay, so Amber, why did I switch to alpha? Why did I go to alpha? Was just because I needed another letter. So I went with another Greek letter. And I did it specifically because I wanted a half of an angle. So I went alpha over 2. But it could have been phi over 2 or beta over 2 or x over 2. It didn't really matter. I just did it so that I now had a half of an angle in here. So Kiva, the reason we wanted half is because we're developing the half angle identities. All right, now I am going to warn you about this identity. And you can probably see why. What about this identity do we have to be careful about? Yeah, the plus or minus. Get a bunch of you throwing that in there right now. We definitely have to worry about that because this will make it either positive or negative. And we know that sine is sometimes positive and sometimes negative. And so the way we're going to know which of these to use is by looking at the quadrants. But there's a follow-up on my warning here, right? This plus or minus is determined by the quadrant, but it's the quadrant of the half angle. Okay, so it's going to be determined by where alpha over 2 is. I don't care where alpha is. Alpha doesn't matter. What matters to me is where alpha over 2 is. Okay, so wherever this alpha over 2 is, like in this case, if it's quadrants 1 or 2, then I use the plus. If it's 3 or 4, I use the minus. So unfortunately, we really haven't had to worry about this with identities yet, right? Up to this point, identities are what they get, or what they are. We did have to worry about the signs when we were plugging them in, but the identity itself never had this. But the half angles do, and there's nothing we can do about it. We just have to make sure we pay attention to where that half angle is located. We'll do an example in a second, help you see how we figure that out. Okay, so there's your half angle for sine. Now, if you want to get your half angle for cosine, you're going to do exactly the same thing, except we're going to start with the power reduction for cosine squared. And the power reduction for cosine squared, the only difference was it was a plus instead of a minus. And so if you go through the exact same kind of derivation, I'm not going to waste our time because you can see exactly what we're going to do. Put in alpha over 2 for theta, blah, blah, blah. What we get is that the cosine of alpha over 2 is going to equal, plus or minus, the square root of 1 plus cosine of alpha over 2. So we'll put a box around that. So the same thing in terms of the plus or minus. It depends totally on where alpha over 2 is, and that's how we choose whether or not to go with plus or minus. All right, so of course we should probably be complete, get a third one, get the tangent of alpha over 2. But same story, start with your tangent squared. You saw that that was equal to 1 minus cosine of 2 theta over 1 plus cosine 2 theta. And if you pull the exact same trick, you're going to get that the tangent of alpha over 2 is equal to plus or minus the square root of 1 minus cosine alpha over 1 plus cosine alpha. Go ahead and put that in a box. And there are your 3 half angle identities. I will show you a couple more for tangent. Tangent's kind of nice. The half angle for tangent has some other forms that are a little bit better. But this is what these guys look like. All right, so again, we're just manipulating the identities we already have. We're just doing some algebra on them and getting them in kind of new forms. So they may feel completely different. They are not. They're just written in a form now that's probably a little bit more useful for us. All right, so let me show you how this works. So for example, let's say I want to know the tangent of 7 pi over 8. All right, so the tangent of 7 pi over 8. 7 pi over 8 is not one of our nice angles. However, it is related to one of them. It's actually half of 7 pi over 4. If you take 1/2 times 7 pi over 4, you get 7 pi over 8. So 7 pi over 8 is half of 7 pi over 4. So what we're going to do is we're going to use the half angle identity, where in this case alpha is 7 pi over 4. It's 1/2 times alpha. So let's go to the identity. This tells me that it's going to be plus or minus, we'll figure that out in a second, square root of 1 minus cosine of 7 pi over 4 divided by 1 plus cosine of 7 pi over 4. All right, so we just plug in our numbers. Now, 7 pi over 4 is a nice angle, and we do know its cosine. What's the cosine of 7 pi over 4? It's on your chart. All right, so Amber just put up root 2 over 2. Good. So the cosine of 7 pi over 4 is the square root of 2 over 2. And we're going to have plus or minus the square root of 1 minus root 2 over 2 divided by 1 plus root 2 over 2. Let me simplify inside that radical real quick. Just multiply everything by 2 to get rid of those fractions. So we get plus or minus 2 minus root 2 over 2 plus root 2. If you feel so inclined, you can rationalize the bottom. I'm not going to bother. Just going to leave it like that. Personally, I think this is kind of pretty. I know it's weird with roots inside of roots and all that, but just the structure of this is kind of cool. I like. But anyway, so there's one more thing we got to figure out, though. Is it plus or is it minus? So we got a 50-50 shot. But let's not guess. Let's actually figure it out. So remember, what's going to determine that is our original angle. Not the alpha, but the half. That means we want to look at 7 pi over 8. So the question is, which quadrant is that in? Where is 7 pi over 8? Quadrant 1, 2, 3, or 4? All right, so I have a vote of quadrant 2, quadrant 4. Now we got a quadrant 3. Anyone want to give me a 1 just to be complete? Okay, so Amber says no idea. Thanks for, I appreciate that. All right, well, let's think about how quadrants break up. So we start at 0. The first quadrant ends at pi over 2. Second quadrant at pi. Then 3 pi over 2. And then, of course, back to 2 pi. So my recommendation with these is just think of the fraction of pi. So look at 7/8. Where is that compared to a half, 1, 1.5, and 2? Okay, so Amber just shouts out 2. So if we're going to go with majority rules, we now have 2 votes for 2, which I guess wins, right? But it is definitely in quadrant 2 because 7/8 is less than 1, but more than 1/2. So we're sitting down here in quadrant 2. It's going to be like down here because we're 1/8 of a pi from making it all the way. All right, so what does that tell us? Plus or minus? All right, so get a couple of people here throwing up the minus sign, and that's exactly right. This is going to be negative because in quadrant 2, tangent is negative. Well, we've actually now figured out the tangent of pi over 8 because pi over 8 is the reference angle to this. So the tangent of pi over 8 is the plus of that. We could use that value to figure out the tangents of 9 pi over 8 and 15 pi over 8, just like we did with any other reference angle. Okay, so that's the trick with these, is you have to definitely watch out, make sure that you get your proper sign, but notice that it came from this angle right here, 7 pi over 8, not the 7 pi over 4. For this specific example, it would have worked out because 7 pi over 4 is in the 4th quadrant, but tangent just happens to be the same plus or minus in quadrants 2 and 4. Had we done this with sine or cosine, that would have gotten us incorrect answers. All right, well, there it is. There are the half angle identities for sine, cosine, and tangent. And this is the kind of thing that we use them for, because now we can find an angle of pi over 8, which means we can find an angle of pi over 16 and pi over 32 and pi over 64. Similarly, we know we already have the angle pi over 6. We can use half angles to get pi over 12, then pi over 24, pi over 48. Basically, it lets us break this down into smaller and smaller and smaller pieces. Okay, well, let me show you 2 more identities, 2 more forms for the half angle of tangent. And these are definitely nicer than the one that we just used. So let me go ahead and build them for you and show you what they look like. So let's start here. We know that the tangent of alpha over 2, I'm going to rewrite it as sine over cosine. So that's just good old quotient identity that we know and love. But now this one, I'm going to multiply top and bottom by cosine of alpha over 2. And if you ask me, why are you multiplying by cosine of alpha over 2, my response is going to be, because it's going to work out. It's a miracle step. So notice what we get. On top, we've now got sine of alpha over 2, cosine of alpha over 2. And on the bottom, we've got cosine squared of alpha over 2. All right. So again, yay. So what? Well, let me do one more thing. I'm going to multiply top and bottom of this by 2. And again, if you ask me why, I'm going to say because I can, and because it's going to work out. But what we just did was we turned that top into the double angle identity for sine. Go back and you look at your double angle identity for sine. I'll write it down here again to remind you. We had the sine of 2 theta was equal to 2 sine of theta cosine of theta. And notice that the top of this fraction is exactly this identity, just with alpha over 2 instead of theta. So if I replace that alpha over 2 on this side as well, 2 times alpha over 2 is just alpha. So on top, this is actually the same as just the sine of alpha. That's pretty nice. Now we're going to do something similar to the bottom, but we're going to remember the cosine of our double angle. Cosine of 2 theta. Now there were 3 different forms of this, but one of them looked like 2 cosine squared minus 1. And notice that's almost what we have on the bottom. We're just off by 1. So if I were to add that 1 over onto this side, again, I can plug alpha over 2 in. And if I plug in alpha over 2 for theta, I get 1 plus cosine of alpha. So there's a second form for tangent of alpha over 2. Tangent of alpha over 2 is equal to sine of alpha over 1 plus cosine of alpha. So we'll go ahead and put a box around that. So we can use this one instead of the other one. And let me just talk about pros and cons. The first pro is that there are no square roots. That's definitely nice. The second pro, and this is the big one, is that there's no plus or minus. We don't have to keep track of where we are. We can just plug in the values for sine and cosine of alpha. And I would argue that that's probably the biggest advantage, is that there is no more, ooh, where are we? Now, the major con is that you need to know both sine and cosine of alpha, where if you look at the other identity, the original form only had the cosine of alpha. So we're basically trading the having to worry about plus or minus and no radical for having to find both sine and cosine. All right. So is that a worthwhile trade? Well, it depends. Depends who you are. All right, well, so there's your second form. The third form is actually found by another miracle step. If you were to take top and bottom of this and multiply by 1 minus cosine alpha, I'm not going to work all the way through it, but this is basically your numerical step. On the bottom, you're going to get 1 minus cosine squared, which becomes a sine squared. And one of those sines cancels with the one on top. And so what this ends up looking like if you do those steps, and again, I'm going to leave that for you for practice, is you end up getting 1 minus cosine of alpha over the sine of alpha. And so same pro and con here as the original one. This one's actually a slightly better because we're dividing by just a number as opposed to a sum of numbers, which can be easier algebraically. So again, just take my word for that, that when you go and you end up fiddling around with these, this third one is probably just a little bit easier if you're going to be doing some algebra. Holy moly. All right. So there are all your half angle identities. So any questions on those? Okay, so how are we feeling? Are we feeling like we felt, what was it that the other day when I asked, you know, how are we? And there was a lot of confused. Are we in that same kind of spot? So Amber gives me a so-so. Hopefully, like I promised, that the more of these you do, the more comfortable you get with it and the less confusing it is. And so maybe today isn't quite as bad because you've seen it, you've already seen it, and you've been playing around a little bit with it. Just realize that all we did today was extending what we did last time. All of these identities come back to that very first picture I drew of the circle. Remember, we drew that circle and we looked at the 2 points and distance thing. That got us cosine of alpha minus beta, cosine A minus B. And after that, everything else just followed from the relationships we have already built. So today was nothing new. Trust me, it wasn't anything new. It was just the same stuff, looking at it in a different way. Okay, well, here's where I'm going to stop with new stuff, but we are going to talk a little bit about the exam that's coming up on Wednesday, because if you haven't been paying attention or you weren't aware, yeah, we have an exam on Wednesday. So let's talk a little bit about what it's going to be on, what you should know how to do, and what to expect. Okay, but before I go there, any last questions on things that we did today? Nope. Okay. So first, in terms of the exam, the time is going to be the same like we did last time. I'm going to make it available to everybody on Canvas at 11 o'clock. So it will turn on at 11. It'll be under exam 2. You just click on it. It should bring you to the PDF. And then it's going to be due by 1:30. So you'll have the 2 hours to take it and the extra half hour of, you know, whatever you're having to deal with technology issues. Okay, so just make sure you upload it via Canvas by 1:30. And it seems like you guys are getting pretty good about the uploading. I appreciate everyone who just does it immediately into Canvas because it definitely makes it easier for me to grade. Anyway, so that's the timing of it. And as such, then we won't have class. All right, no class on Wednesday. Our next class will actually be on Monday, where we'll just build a couple of more identities. I know. So yeah, the exam is in 2 days, as in, yes, this coming Wednesday. Anyway, so we're going to develop just a couple of more identities, and then we're going to use them to help us solve equations, because that's really where we're going with all of this, is being able to take equations that involve trig functions and solve them. Okay, so that's what we'll do Monday. But as for the exam, what it's going to cover. So it's going to cover chapter 8. And chapter 8 was the graphs of all of the trig functions. And also then that included, you know, amplitude and period and phase shift and stuff for the sine and cosine. Chapter 8 also included inverse trig functions. So the things that you're definitely going to need to know how to do from chapter 8 are, if I give you an equation, be able to tell me amplitude, period, phase shifts, all that good stuff. If I give you a graph, you need to be able to reconstruct the equation. I could give you some data, right? Like temperature data or sunlight data or something else that's sinusoidal, and ask you to build me an equation that matches it. So hopefully you remember when we did those kinds of problems back in the day. So know how to do all that with sine and cosine. For the others, it's important to be able to recognize what they look like. Obviously, we didn't do as much with them, but you definitely should be able to figure out their periods, which is a matter of looking at how often they repeat and then adjusting it properly. And the basics of what their graph should look like. Okay, so, and then with the inverse trig functions, definitely remember the restrictions. I can't stress that enough. Know the restrictions for the inverse trig functions for the big three, because that's super important when we use them, so that we make sure that we're getting the correct angle, even though we may be finding one that's not in the right restriction. So know the restrictions. So if I were to give you an angle, or sorry, a trig function value, you should be able to tell me what the inverse trig, what angle the inverse trig will give you, be able to go to the correct quadrant if it's not the one you want. Also be able to do the composition. Now, a couple of things I just want to state about this part of the exam is you must show your work. Okay, you can't just give me an answer, because technology will do that. I want you to show me, you know, how to get to that answer. So I am going to be looking at your work. It's not going to be enough for you to go, oh, sine of sine inverse of 5 pi over 3 equals, you know, minus pi over 3. No, you're not going to get full credit because you didn't show me how you got to that. All right, so this is one of the things that's going to be a little bit different, and it must be because of how this our current situation is. Since I can't give you an exam that doesn't have calculator part to it, you got to show me your work. Okay, so I am going to be a stickler about that. I normally am not, for those of you who know me, so just be ready for that. But anyway, so be able to do the composition and also be able to do the mixed composition, meaning things like the cosine of inverse tangent of 2/3 and the like. But basically we had two approaches. One was to draw the triangle and then put the pieces together. And then the other was to use the identities. But again, most important things in there, twofold. One, restrictions. Know your restrictions on the trig functions. And also watch your signs. Watch your plus or minus signs, because those both matter. Okay, so chapter 8, and then it's also going to have the first two sections of chapter 9, which is identity stuff. 9.1 was when we first just started playing with them, proving identities, using the ones that we already knew, right? So making use of the algebra, so the factoring, the fractions, all that, Pythagorean identities, turning everything into sines and cosines, and so on. That was 9.1, and then 9.2 is the sum and difference of angles. So it's not going to include anything we talked about today, but it will include what we talked about last week. Okay, so the sum and difference of angles identities, know how to use them, know how to apply them. This is another one where you're going to have to show me your work. Because like if I ask you to tell me the sine of 11 pi over 12, you can't just give me what your calculator tells you. You're going to have to show me how you got it using the identities. Also on that note, when I ask for trig function values, give me exact values. Don't give me decimals. I know that this happened for some people on quizzes, and I made a lot of comments on quizzes about this, but I just want everybody to know this. If you write, for example, square root of 2 over 2, that's the exact value of cosine of pi over 4. But if you were to write cosine of pi over 4 equals 0.707, that's false. That's not true. That's an approximate value. And even if you give me 1,000,000 decimal points, it's still an approximation. It's a really good approximation, but it's still an approximation. And to a mathematician, no, I want the answer. And the answer is root 2 over 2. Okay, so I will probably try to be a little more clear in the wording. So look for things like give the exact value of. And so if I say that, that means don't give me any decimals. Really, we reserve decimals for when it's an applied problem, because, you know, like an engineer is not going to care that the height of the truss is 16 root 2 over pi. They're going to want to know what that length is, right? So, but for math, I want exact value. So I'll try to be a little more clear just so you know what to expect. So just another thing to watch out for. Anyway, so that's what that exam is going to look like. I don't imagine any of you are going to run out of time, because it's we didn't really do a ton of stuff, but it's enough that I want to make sure that we're all on top of it. So anyway, so that's the plan for Wednesday. So any questions about that? All right, well, hearing none, I'm going to go ahead and stop the recording here.